Hello, everyone, and welcome to Astronomy on Tap with the Scobie Education Center, where we gather together once again to hear some amazing speakers talk about how they explore the universe while we toast to the universe. My personal choice is Coke, so don't forget to grab your favorite snack or drink. And while we listen to these amazing speakers talk about some of the wonderful things that they have discovered with their research. So allow me to introduce to you our first guest speaker. His name is Sam Hart, and he's going to talk to you about how solar activity influenced wheat prices in England during the Renaissance era. He is a second-year Ph.D. student at the University of Texas in San Antonio and his joint graduate program at Southwest Research Institute. And he received his bachelor's degree at the University of Montana in 2018, and he specializes in heliophysics and magnetospheric physics, forgive me. So with that, Sam, would you like to join us?
Hello?
Yes.
Hi. Thank you very much for the introduction. I will start to share my screen. Hopefully it works. Let me know. Do you see it full screen?
Indeed we do. Go
okay,
ahead.
Good. Hello, everybody. As Michelle said, my name is Sam Hart. I am a second-year PhD student at UTSA, and I'm going to be talking to you guys about the influence of solar activity on wheat prices in England during the Renaissance era. So let's just jump into it. To start, we have to go back, there we go, 10 billion years ago. 10 billion years ago, the solar system was in its early stages, and suns were constantly, or stars for that matter, were constantly exploding. And when stars explode, it's called a supernova. And supernova, like this picture, are very pretty to the eye, but they also leave a very distinct signature throughout the universe called cosmic rays. And remember that term, cosmic rays, because we will come back to it shortly. So let's fast forward to the 1800s with William Herschel. William Herschel was a European astronomer, very well known. He did some great things. He discovered what he called the Georgian star, which we now know as the planet Uranus. He was a huge pioneer in discovering nebula and galaxies, where he discovered and documented over 2,400 nebula and galaxies. At the time, he thought that other galaxies resided inside our own galaxies. But later on, they figured out that was not the case. And he also proposed, he was one of the first to propose that our galaxy was actually a disk shape. We know now that it is a spiral galaxy, but he was one of the first to say that it was actually flat and not round, as some had thought. And then the purpose of this talk, one of the more interesting things that he did was he observed a correlation between sunspot number and wheat prices in England between the 13th and 17th century. So what exactly was he observing? So here's two pictures of the sun. And on the left is a picture of the sun where the sun has no sunspots. We call this to be solar minimum. Very little sunspots on the sun. And when this was the case, he noticed that wheat prices were much higher than they are normal. Whereas on the right side, we see a sun with a lot of sunspots. And when he observed this phenomenon, he noticed that wheat prices were normal and there was nothing irregular going on. So he made this observation, and he himself was a little skeptical, and he wrote in his paper, "This prediction ought not to be relied on by anyone. It is a very large leap to go from the sun changing a little bit to massive increase in wheat prices." And he was ridiculed pretty heavily for it because of how well respected he was. I am not so well respected, so I can take the criticism. So what exactly was going on in England during that time? So here are a few images. I'll go through each of them one at a time, so they're not all that scary. On the left here is a graph of wheat prices between the years 1260 and 1710. And it's actually plotting the difference in wheat prices from year to year. So the highest points on this line are times when the wheat prices were incredibly high compared to that of the previous year. And if you look at some of the years, you can see that, they happen maybe between every 10 or 20 years. The largest increases. For this study, the people that originally did this omitted the two times in surrounded by the white rectangle. The first time because of the Dispenser War, where they overthrew and possibly murdered King Edward II. So there was a lot of political turmoil. And then the second one, there was a huge economic crisis where they had way too many workers and there were a lot of rebellions. So those times were omitted for this study. So if you take each number and subtract the last time there was a price burst, you receive this histogram over in the top right. So this is a histogram of price burst interval. So what was the time between when wheat price was incredibly high to where it was normal to where it was high again? And you see that happens actually roughly about 10 to 11 years on average. And then if you look right below it, here's a histogram of sunspot minimum to sunspot minimum intervals, which is also on average between 10 to 11 years. We know now that that is the time of the solar cycle. We have studied this in great detail, but back then, Herschel didn't even know the solar cycle, so he wasn't too convinced by this. But you see that the histograms are incredibly similar, and so this definitely warrants further analysis. But it's still too much to just say one caused the other. We need to know how, and so that is what I'm going to do next, is talk about how. So remember, we talked about cosmic rays on the first slide. So cosmic rays are particles accelerated to basically light speed by supernova shock blast. Supernovas are the largest explosion that we see in our universe. And when they do explode, they create the highest energy particles that we even observe. We call them cosmic rays. And they go all over the universe. And we see them all the time. And actually, they are a very harmful source of radiation in interplanetary space. So when we send astronauts to the moon, like we did in the 60s, and hopefully soon again, and soon for Mars as well, we will have to take into account cosmic rays as a potential harmful source of radiation. So what does the sun exactly have to do with cosmic rays and vice versa? So when the sun is in solar minimum, we can think of it, or when there's no sunspots, we can think of it as though its defense mechanisms are down. Cosmic rays cannot easily get into our solar system because of how, big of a beast our sun is. But when our sun has no sunspots, it's pretty timid, and so cosmic rays can enter into our solar system very easily. And so you see this from the image on the left. The sun, no sunspots, is really not doing much, as we could see from this yellow to fade to black. And so the cosmic rays can really easily get to Earth. On the contrary, when the sun is at maximum, you see with all this excess light and whatnot, it's pushing back on the cosmic rays. Its defense mechanism is up. And when that happens, from my little animation here, the cosmic rays do not actually make it to Earth. And this is not just theory. We actually observe this. So here's some figures. On the bottom here, we see the sunspot number on the sun. And when the sunspot numbers are very small, here's the solar cycle I talked about earlier. And when the sunspot numbers are very small, we see that the cosmic ray background is at its highest. So we know that when there are no sunspots, we are seeing on Earth a lot of cosmic rays. So what exactly happens when a cosmic ray reaches Earth? Well, it does something, in my opinion, really fascinating, and that is called a cosmic ray cascade, is what we've coined this term. And this is a good representation of what a cosmic ray cascade is. We don't actually see this, but this is actually what is going on. So a cosmic ray comes in from 10 billion light years away, however long it took to get here. And it traveled all this way. And when it reaches Earth, Earth's atmosphere is denser than most everything in the solar system. You know, the solar system is a vacuum, but we breathe in air, and that air is very dense. And so the cosmic rays are coming from the universe, and they hit the top of our atmosphere. And they have such force to them, such large energies, that they explode into a billion different types of particles that we call the cosmic ray cascade. And all of these particles shower down into Earth's lower atmosphere. So this is really interesting because when you input or when you inject a bunch of particles into Earth's lower atmosphere, you can aid in the formation of clouds. And so that's actually what's going on here is from this image, you see that the cosmic ray flux given by this solid black line, when it is at its highest, so too is the amount of cloud cover given by these points. So the more cosmic rays incident on Earth is shown by larger amount of clouds in the sky. And so when you have a lot of clouds in the sky, you can get, more rain and more snow. And so what was going on in ancient England, or ancient 13th to 17th century England, was that when there were no sunspots and they were getting hit by a lot of these cosmic rays as a result, they felt that in more clouds and more snow and more rain. And snow and rain can greatly influence how much wheat is grown during a certain harvest season. And with a lot of snow and a lot of rain, you can delay your wheat harvest. And with less time to grow your wheat, you grow a lot less wheat. So the wheat harvest was very terrible. And as a result, the prices increased dramatically to meet the demand. So to summarize, with some nice images that I got off of Google, when you have no sunspots, you get more cosmic rays coming from the universe hitting Earth. And the more cosmic rays means more clouds. More clouds is more snow and rainfall. More snow and rainfall translates to worse wheat harvest. And the worse wheat harvest translates to higher wheat prices. So you might be asking yourself, do we see this elsewhere, or is this really just in England during, the Renaissance era? Well, recent studies have shown that cosmic rays don't actually translate to cloud cover on a global scale. This is a very regional effect for England and some other parts of the Earth, but as a whole across the globe, we really don't see this relation here. As a matter of fact, if you actually look at this, it is only if you increase your cosmic rays to as much as you can, you really only see just 1% increase in the cloud fraction, which is very small to begin with. And so we really don't even see that 1% on a global scale. So why was this very minor climate effect so apparent in England's wheat prices? Well, it really has less to do with the amount of cosmic rays or cloud cover than it had to do with the wheat market as a whole. England's wheat market, little did they know, was pretty much on the brink of disaster every year. They were barely making enough wheat to feed the population as is. So when you take this really small effect of increased cloud cover, you really only need one or two more heavy downpours or 12 more inches of snow to really screw over your entire wheat harvest. But because it is a talk about Earth's climate, it definitely does not come without some controversy, and I will get into that controversy right now. So here is a plot of the last 400 years of sunspot observations on the sun. And you see between the years of 1600 and about 1800, we went through what is denoted Maunder minimum, because it was found by Maunder. I don't remember his first name, but we call it the Maunder minimum. And during the Maunder minimum, there was a lot of reports of colder weather, harsher winters, longer winters. And so we say that during the Maunder minimum, we went through a little ice age. And if you believe everything that I just said about cosmic rays increasing cloud cover, you see that with a huge time frame with no sunspots, you would get a lot of clouds, and with a lot of clouds, you'd have a lot of rain and snow, and therefore it would be really cold all the time. But during that time, there was also an increased amount of volcanic activity. And so volcanoes, very similar to cosmic rays, volcanoes will create a lot of smoke. Smoke will rise, help aid in cloud formation, and then you would get more clouds, more snow, more rain, cooler weather. So these are two possibilities that could have caused the little ice age during the Maunder minimum. But there are a lot of papers, some siding with cosmic rays and some siding with volcanic activity, and they are very passionate about which is which. The cosmic ray people, they will say that, the people who said that there was volcanic activity just can't accept the fact that cosmic rays work on a global scale, and the people who believe that volcanic activity happened during this time say that the cosmic ray people are misusing statistics. They are leaving out important information when they create their papers, and there's a lot of personal insults if you talk about the little ice age. But we actually are soon, hopefully, going to get an answer to this problem. If you look at present time, you will see that the maximums of all these sunspots has been going down periodically over the last 50 or so years. And if we continue this trend, we might actually head toward another Maunder minimum, which a lot of people are calling the new grand solar minimum. And if this happens, we will actually see our temperature is going to go down. And if we go into another little ice age, well, maybe we are actually feeling global effects to cosmic rays. Hopefully, though, we don't see any volcanic activity during that time, because that would just lead to more confusion. So that actually concludes my talk. Thank you very much for having me. It was a pleasure giving this talk. I had a lot of fun. And if you have any questions, let me know. I would be happy to answer them.
All right, Sam, thank you again. That was a very interesting talk. All right, so if you are here with us on Zoom, leave your questions down in the comments, and we'd be more than happy to answer your questions. So our first question for this, what spurred your curiosity on this particular topic, and was it hard to find a lot of research on this particular topic?
So it definitely was not hard to find a lot of research, because this is a topic on Earth's climate. There's a lot of people who are very passionate about that subject, and so there's no shortage of information, at least that I saw. What sparked my curiosity? I was reading a paper on the discovery of the solar wind, which that's a talk for another time. But when I was reading a paper, I saw a sentence about solar activity and the London Grain Exchange. And I had just never seen anything like that before in a paper. So the first time I read it, I actually thought that I just read something wrong and that I wasn't going on. I didn't know what was going on. But then I went back and I read it again, and I was like, oh, solar activity and wheat? And so I started looking into that, and I mean, I opened up a huge can of worms. And so I I just started reading that for the last like month, and I thought that I would tell all you guys about it.
Awesome. Question from a viewer. He says, what are the red X's in the previous plot?
Oh, should I share my screen again? Is that okay?
Yeah, go ahead.
Okay. Oh, it's actually still on the slide. So I'm not 100% sure what happened here, but the blue line is just a measure of sunspot number. Every month or so, they just calculate how many sunspots they saw total and plotted them on here. And they did the same thing between 1600 and 1750. But I think the time between each measurement was different, so they decided to denote those as red X's as opposed to blue lines. But it's just the same. It's just the amount of sunspots that they saw at the time of the measurement.
All right, next question. What is the cosmic ray interaction and the catalyst for the cosmic rays?
Okay, I think.
Yeah, what is the cosmic ray interaction that catalyzes cloud coverage?
That is a good one. So oftentimes when you are creating clouds, clouds can, the water vapor molecules in the sky or ice molecules will cling to, some solid in the air or some particle, some dust particle in the air before it actually starts the cloud formation. So if you have some ice, it'll cling to this solid in the air. I believe they're called aerosols. And those solids in the air, basically the more you have, then the more the ice crystals can combine to those or, like attach to those. And so it makes it a lot easier for these ice crystals to pile up and start forming these big clouds that we see in the sky. And so what the cosmic rays are doing is when they cascade, like this image, they are putting in so many of these dust particles into our atmosphere that it's really easy for these ice crystals to connect to the cloud or to connect to them and form clouds very easily. So that is the general gist of how cosmic rays actually help aid in cloud formation.
Okay, next question. Where do you see this research going, and would you like to extend it to, and where would you like to have it see it go from here?
Well, personally, from this image where I said we're heading toward possibly another long minimum, I would not necessarily be opposed to that. So I hope that our sun decides to stop producing sunspots, because that would be pretty interesting to see if, because we would certainly know the answer to whether or not cosmic rays can actually do this or not. Even if this does happen, we won't see any massive decrease in wheat prices in England, though, because nowadays with genetically modified foods, you could get like multiple harvests a year and you have a huge surplus. And if you do actually somehow have a shortage, then with the international food market, America, Wyoming is a massive state that really only grows like hay and wheat. So we would be able to help them out. And so they wouldn't really see much of an effect to that. But where I would like to see the research go is definitely more all-sky surveys of cosmic rays possibly aiding in cloud formation, because that is the biggest uncertainty, is really how much of an effect do cosmic rays have on cloud formation. So more studies like this is what I would be interested in. And if I could do it, I would definitely help.
Okay. Next question is anyone modeling both of these hypotheses together? And if so, do you know who?
I am not sure on who, but I do know that when it comes to cloud formation, there are a lot of different processes involved. Like to say that cosmic rays are the only things that help aid in cloud formation versus volcanic activity. it's hard to say, but what we can do is we can just measure how many aerosols, the term that I mentioned previously, are in the sky, which I believe is constantly happening, but linking that to cloud formation has not been really done to such a grand scale yet. And so that is, I think, what people would look toward to help produce a model of predicting cloud formation in the future.
Awesome. A question from Facebook. It says you said cosmic rays didn't affect cloud coverage on a global scale. So why England? Is there something special about their location, or were they just lucky?
That is a great question. I definitely was reading a lot about it, and I would say that nobody can say for sure what it is about England that caused cosmic rays to be able to affect clouds, but everybody seemed to agree that England just has a predisposed ability to get affected by cosmic rays to make clouds. We're not too sure why we don't see it on a global scale. I struggle a little bit with that. And so I really was looking at this, and this graph can actually be a little misleading because the change in cosmic rays is huge. It's like a 15% difference in cosmic rays from max or minimum to maximum. But in the cloud coverage, it's only like 2 to 3%. So you really need a lot of cosmic rays to change the cloud fraction really slightly. And so there just must be something about England that we actually do see a little bit of a correlation as opposed to the rest of the world where it's just not there.
Interesting. Next question is this. I heard another presentation that the melting of the polar ice caps also impact the path of the Gulf Stream at the time of the Mater's minimum. The combined effect was the mini ice age of Northern Europe. What are your thoughts? I see the wheels turning.
Yeah. So when I first was reading this, I knew about the Maunder minimum. And so I was like, well, I know that there was a little ice age during the Maunder minimum. So if you believed in cosmic rays' ability to potentially cool down the Earth, then it makes perfect sense. And so I started researching a little bit about the Maunder minimum, and I found that there are several, the volcanic activity and now the polar ice cap melting, that, there were multiple other things going on at the time to create a little ice age. And so it's really hard to say which had the most effect, but it seems as though there are multiple things had to go right or wrong, depending on how you look at it, in order to get the little ice age that we observed. But I'm not too sure what would have happened in the 1600s to cause a melting, significant amount of melting in the polar ice caps. That's just my initial thought. But I'm definitely not ruling out that was a possible aid in cooling off the Earth in Western Europe, anyway.
All right. Next question is the audience member asks, what exactly is a sunspot?
Wow, that is a loaded question. I'll just go back to a little picture. So a sunspot is just this small point on the sun where, think of it like a boiling pot of water. And we see a lot on the boiling pot of water, you see a lot of bubbles rise up to the top. And so think of a sunspot as one of those bubbles. So you get this really hot gas that comes up, and then it wants to go back down, but it's restricted to going back down. And when it does that, it cools off. When the bubble comes up to the top of the boiling water, it's colder at the top than it is at the bottom. And so, but these sunspots are restricted from going back down, so they get really cold. And when they're really cold, they don't emit nearly as much light, and so they look like a big black spot on the sun. But they are a signature for solar activity, because a sunspot can often result in a big explosion. If you get a lot of, if it's trapped there, its tension keeps rising until eventually it just explodes. And that explosion pushes a bunch of stuff out into our solar system, which is actually why we don't see a lot of cosmic rays, because we're pushing so much out that cosmic rays can't really get back in. So the sunspots are just this little bit of the sun that is stuck where it is and it can't go anywhere, and it cools off, and then eventually it explodes.
Yeah, I know sunspots are sometimes often tied with the magnetic field of the sun. Mm-hmm. And usually where you have a sunspot is where you have high concentrations of a magnetic field.
Mm-hmm.
So
and
those are also correlated as well.
It likes to trap a lot of things in a sunspot. If you get in a sunspot, you probably can't get out until the sunspot decides that it's time to explode. It's pretty much how it goes.
All right. Are there any more questions?
If not, I had a wonderful time. And so I love giving this talk, and I thank you guys a lot for listening. Thanks, Michelle, and I hope you guys enjoy Tracy's next talk. She's got a lot of cool videos on it that I saw.
Awesome. Definitely. I know, actually, and somebody mentioned happy birthday.
Oh, yeah. That is my brother, and tomorrow is my birthday, and I would not want to spend it any other way than talking about astronomy.
Well, cheers and happy birthday.
Thank you.
All right. Thank you again, Sam. Our next speaker is Dr. Tracy Becker. She is a planetary scientist at Southwest Research Institute right here in the heart of San Antonio. So we get to explore the cosmos from our own backyard. She is a co-investigator and serves the composition working group for NASA's Europa Clipper mission. And her research interests are studying asteroids, Saturn's rings, Jupiter's moons, and ultraviolet wavelengths. And she's also a fellow solar system ambassador like I am. So Dr. Tracy Becker, take it away.
Awesome. Thanks, Michelle. Thanks, everyone, for joining tonight. I'm going to just set up my screen here. Hopefully hit play. All right. Hopefully you can all see my slides.
We most certainly can.
All right. Okay. Hi, everyone. As was just said, I'm Tracy Becker. I work here at the Southwest Research Institute here in San Antonio, for those of you who are local. I wanted to first start out by saying this Astronomy on Tap is a program that Vincent Hugh, a colleague of mine, and I started in the San Antonio location a couple years ago now. This is a program that goes on all over the world. We certainly miss meeting with everybody in person, but there's, of course, a cool benefit to being virtual and getting to spread the science to everyone who's interested and not just necessarily local to San Antonio. But a huge thanks to Scobie Education Center for sort of carrying the torch on this program and helping us make this a virtual program as well. At some point, when all of this is over, we look forward to seeing you all in a local location again. In honor of Blue Star Brewing, which is where we usually have it. Oops, it's in the plume. You can't see it. Cheers to Blue Star. And everyone, a big cheers for Astronomy on Tap tonight. So we start our journey today at Jupiter. So this is an incredible image of Jupiter from the Juno spacecraft, which is actually also operated. The science is operated out of the Southwest Research Institute here in San Antonio as well. But we're going to take you all on a journey to Jupiter's exciting moon system. So Jupiter has a ton of moons, actually, many, many dozens of moons. But Io, Europa, Ganymede, and Callisto are sort of the primary moons that we're going to focus on. But you can see there's almost an entire solar system of moons orbiting around Jupiter. And we're going to talk about these moons in part because they're known as the Galilean satellites. Io, Europa, Ganymede, and Callisto. And they're known, there's a very specific reason that they're known as this. Not only are they the largest, but they were the first to be observed by Galileo with a telescope. So back in the late 1600s, when Galileo was able to, or early 1600s, when Galileo was able to observe started using telescopes, he observed these moons of Jupiter. And you can actually do the same. If you use a fairly decent telescope or even a good pair of binoculars, you can actually look out and see Jupiter and see 4 dots that sort of follow along the equatorial, near the equator of Jupiter, but further out. And those are these Galilean satellites. And you can do that even, it might be a little bit too late tonight. Actually, if you ran outside, maybe during my talk, it's on the western horizon now, sort of just before sunset. You can look out and you should be able to spot Jupiter and Saturn nearby. But these moons have an important history. It's cool because Sam gave an awesome presentation and talked a lot about the history of how astronomy relates to our own world. And so this was really a critical measurement that Galileo made, was seeing these Galilean satellites, because this was the first time someone could actually prove that objects were orbiting something other than the Earth. So you might have a friend or two that thinks the whole universe revolves around them. That's what we all thought, apparently, back in the day. There was the heliocentric model, which was that the solar system actually orbits around the sun, but that was heresy to actually say. So Galileo proved that there were objects orbiting other objects by looking at these moons and seeing how they changed each night and basically going around Jupiter. But as a result, he went on house arrest for the rest of his life. So, oops. So we have to be grateful to him for identifying these Galilean satellites, Io, Europa, Ganymede, and Callisto, but we're going to focus primarily on Europa. And why Europa? So Europa is known as an ocean world. And if I could have a chat feature, I'll let people shout it in the chat or just shout it out loud if you want. But why would you think we're interested in an object in our solar system known as an ocean world? This might be a fairly obvious answer, but the answer is life. When we see water on Earth, anywhere that we see water on Earth, almost everywhere, we actually are able to find life, even in some of the most surprising places in the darkest, deepest parts of our ocean. We still have managed to find life. And so that's really what drives us to explore these worlds in our solar system that we know have some sort of liquid body, especially when it is actually H2O. And that is the case for Europa. And so NASA's next really big mission is this mission called Europa Clipper Mission, a journey to an ocean world. And the goal here is to assess the habitability of Europa. So the idea is that they're going to make all these measurements, and I'm going to talk about that tonight with you. But all of these measurements are meant to understand whether or not life could be, or maybe even was, supported on Europa. And the key term, again, is supported. It is not necessarily meant to identify the existence of life, but it is meant to try to understand if the conditions there are good for life as at least we understand it, or we think we understand it. And so I want to talk briefly about why we think we know what we know. When we see Europa, how do we know that there's an ocean world? How do we know that there's actually liquid water? The first evidence actually just comes from looking at it. So it's extremely bright. It's very reflective. Basically, it looks like water ice when we look at just a regular telescope. More importantly, when we look at the spectroscopy, when we look at how each wavelength or each energy of light bounces off of Europa using telescopes like the Hubble Space Telescope, we see that it reflects light in a way that's very similar to water. So this is not just a brightness measurement. This is actually at very specific wavelengths of light, what it looks like in our telescopes. And lastly, it's a very, what we call a young surface. So there are very few craters on Europa. We saw this way back when we first started sending our first spacecrafts out into space that flew by Europa. We were able to see it is fairly smooth. Why would Europa have no craters? But the neighboring moons, Galileo, Callisto, why do they have craters? There's no reason that Europa should have fewer craters. So the answer probably is that it's more like the Earth, where we actually have the ability to resurface through plate tectonics, through the ocean. They basically degrade away any crater impacts that we might see. So just like the moon is riddled with craters, the Earth is probably in the past would have had a lot of impacts. Of course, we have our atmosphere that also protects us, so it makes it a little bit different. But even the smaller impacts that we've had in the past get washed away with time. Okay, so that tells us a little bit about something going on, but how do we know the actual interior of Europa has water in it? This was actually predicted mathematically. It was predicted before any spacecrafts went to the Jupiter system. There was a prediction made by a scientist who said that the interior of Io, because it's so close to Jupiter and getting so much tidal pressure from Jupiter, basically, that just like our moon and our Earth kind of tug on each other, Jupiter is so massive and so close to Io, and it tugs on Io, that basically keeps the interior of Io warm. And in fact, when we flew by Io, and these images are from a more recent flyby of the New Horizons spacecraft, we actually saw active volcanism. We actually see sulfur spewing out of Io at the top there. So we know that this is a reality. Europa is the next moon out. It also has a lot of tidal forces acting on it from Jupiter, but also from the other moons around it. So mathematically it sort of works, but okay, that's one line of evidence. That doesn't really tell us for sure that it's happening. What happened was actually, and this gets a little bit technical, but basically Jupiter has a really strong magnetic field. And when the spacecraft Galileo, which flew out in the 1990s, flew by Europa, it noticed this deviation in that magnetic field. And the only real explanation for that deviation to happen when you're close to Europa is that Europa has its own counteracting magnetic field, essentially, which can only be produced by having some sort of a liquid core, especially one that has some sort of salt. So it has some sort of liquid, sorry, and when I say core, I meant to say liquid body inside. It doesn't have to be the core. It's not generating its own magnetic field like the Earth, for example. It's actually just counteracting the magnetic field that's encompassing it from Jupiter. So we actually see this way, this is the evidence that we see this subsurface salty water ocean. And we think that there's a lot of water there. So the ice shell is probably 10 to 15 miles thick. And underneath that, we think that there's a water layer of 50 to 100 miles. And then you get the rocky layer, and then you get a metallic core. This amount of water that we're calculating is twice as much liquid water as in all of the Earth's oceans combined. So it's a lot of water. So of course that makes us excited to go and explore it a little bit more. Not only that, we look at some of the images that we had. And again, think about this. This is 1990s technology, cameras that we had back then with Galileo. So just imagine what we're going to get when we get there in the next decade. There are these features, these features called lineae, which we think might be regions where the ice shell is separating and water can actually come on out and fill in and freeze and basically like plate tectonics on Earth. We also see these chaos regions, which we think might be these big chunks of ice that have turned over or have been muddled in some way that we don't fully understand yet. And this is a close-up of those, some of those lineae features. So these things are really, really wide, 20 kilometers wide, and a few hundred meters high. So it's a really, really incredible feature that we're going to be able to see when we get there with the Europa Clipper. And importantly, we also do think we've seen water plumes. We've seen a few different detections using the Hubble Space Telescope, looking back at some old Galileo data. There's a lot of evidence for possible water geysers or plumes coming out of part of Europa. And this sounds maybe kind of exciting or crazy, but I already showed you that picture of Io. And when we got to a small similar moon called Enceladus around Saturn with the Cassini spacecraft, we saw exactly that. These are real pictures from the Cassini spacecraft of water plumes coming out of the South Pole of Enceladus. So they're real in the solar system. The question is, are we going to make sure can we be seeing them when we get there with Europa Clipper? Are they certainly happening, and do they happen all the time? These things might turn on and off, so hopefully during the mission we'd be able to see them if they're there. And so that's the goal. We're going to go to this moon and assess the habitability of Europa with NASA's Europa Clipper mission. And what we need to do is assess the ice shell, the ocean, look at the composition of the surface and the atmosphere, understand the geology and how it connects to all of these things, and look for any current activity like plumes. And I want you to note the array of expertise needed for a mission like this. We need astrobiologists, we need geologists, we need spectroscopists, people that study the way light gets reflected. We need people who understand different instrumentation, radar instruments, and UV instruments. So there's a whole array of people that need to be involved to make this happen. And that's not even to talk about the engineering, the diverse set of engineers that we need to make a mission like this happen. So if you're interested in anything like this, there are so many roles and ways to be involved in NASA missions. So it's a really exciting time for a lot of people. And again, that ultimate goal is to assess the habitability of Europa. On the right, you can just see this is maybe an idea of what we think we're going to see when we get there with Clipper. This is what we sort of picture is the inside of Europa, but you know what? We don't know. There is so little that we know, and my guess is that when we get there, it's going to just completely surprise us. There's going to be so many guesses and surprises and things that we never even thought of. On the left, this is actually a picture from some of the deepest, darkest parts of our ocean. These things are sometimes called black smokers, and these are basically vents coming out that actually end up supplying the energy that's needed for life to exist. So, you usually associate life with sunlight and being able to eat the plants or anything like that, or being plants and having photosynthesis. But actually, these hydrothermal vents at the bottom of the Earth's ocean can actually supply the energy needed for these critters and things to live at the darkest, deepest part of our ocean. So if here, why not there? And so the Europa Clipper mission is approximately 3-year mission with a bunch of flybys of Europa. So we're going to fly by Europa a bunch of times. We're not going to orbit Europa, and that's important because we can't. I mean, we physically could, but the problem is I mentioned that Jupiter has this really, really strong magnetic field, and it causes this very dangerous radiation environment. And it's not only would it be dangerous, for example, for a person to be standing on top of Europa for a variety of reasons, but it's dangerous to our spacecraft and our instruments. It basically will break them down eventually. And so the idea is what we'll do is kind of fly pretty far out from Jupiter and then get out of this at least the most intense magnetic field part of Jupiter's field, and then come in and do a nice quick close flyby of Europa, and then get back out, send some data back down to Earth, and then do another flyby. So this is why we kind of have this plan for how we're going to observe Europa. And a quick video here just to show one of the things we really want to do is understand the depth of the ocean ice, that salinity or the temperature of the ocean, and understand how the surface and the ocean might be exchanging material. So if we see stuff on the surface, how does that relate to what's below? And I think I didn't skip it. Okay, yeah. So and the composition, we want to understand what all of this kind of red milky stuff on Europa is. We think it's some sort of salt material, but we don't really know exactly what it is yet. Most of the rest of Europa surface is water ice, but we want to know what else is there. That'll also tell us kind of how plausible it might be for life that we understand to exist if we know what kind of salt and how much of that salt exists. We need to study the surface, and we're going to study the very tenuous atmosphere. It doesn't have an atmosphere like Earth, but it does have a little bit of an atmosphere. And we want to study the geology. I remind you again, the photos we're going to get with the way that cameras have evolved since the 1990s to now, you're going to expect some really incredible pictures from this mission. And lastly, we're going to keep searching for plumes. So we have instruments on board. The UV instrument, which is the one I work on directly, is being built right here in San Antonio. This is what we call the plume hunter. It's one of the best devices to find the plumes. Another instrument being built right here in San Antonio is the mass spectrometer, and it's sort of known as the sniffer. So it can actually take in the gas and understand exactly what the gas is made up of if we fly through a plume or if we're flying through the atmosphere. And we have an instrument that kind of can taste the plume. So it's a particle detector that's being built at another institution that can basically collect particles and understand more about them. So if the plume is spewing out gas as well as some ice particles, we'll know what's coming out of these plumes. And so we have a big array of instruments. This is a huge team, really wonderful people to work with. But this is kind of the next big mission, tentative launch in 2024. And we hope to arrive in the late 2020s. So we hope you stay tuned. And this is the science team right here. And you can follow more about the mission, of course, on Facebook, Twitter, wherever. So thank you all so much for listening to this talk. And I'm happy to take some questions.
All right. Are there any questions? Thank you, Dr. Becker, for that amazing talk. I know several of my team members are like, oh, wow, we need to get some more information from you because we're working on a virtual Europa mission for our Challenger Learning Center. So they might be in contact with you. So
awesome. Yes, definitely.
All right, so question number 1, since Europa, Ganymede, and Callisto are thought to have oceans, why is Europa the most significant to study?
That's a great question. So Io's ocean is not water, so that one kind of rules that one out fast. Io is still certainly an interesting place to go. I think the other moons, the evidence for the oceans in some ways is a little bit more limited, and also it's a little bit less known how much exchange there might be with the surface. So how easily is it going to be studied? So for the exact reasons I was talking about, where we see this resurfacing on Europa that we think must have happened somewhat recently. We really think that kind of information is going to give us more clues to the inside than some of these older surface moons that may also harbor water inside as well. Now, that said, this was just one specific mission designed to go to this moon. That doesn't exclude those other moons from being fascinating. And in fact, the European Space Agency is sending a spacecraft to those moons. It's called the Jupiter Icy Moon Explorer, or JUICE. And that mission is planned to go and study all 3 of these outer moons. Again, they're not going to Io because, again, the radiation gets even worse at Io. But it's going to be studying Callisto, Ganymede, and Europa. So there is definitely scientific interest everywhere, but you got to pick your battles, right? You can only do so much in one mission.
All right. And next question is maybe a little off topic, but are there any plans by NASA to do any search for life on possibly Titan?
Ooh, there are definitely plans to understand Titan better. So there's actually a really exciting mission upcoming called Dragonfly, which is a mission being led by an awesome scientist, Zibby Turtle. She's leading this mission to basically fly like a quadcopter type thing across Titan. And so Titan, of course, is Saturn's moon, and it sort of has seas as well, but these are methane seas and not water. So there's definitely interest in what kind of life or habitability that moon has. And it has a much thicker atmosphere and almost like a water cycle, but again, with methane and ethane. But that mission, I don't know if that's officially labeled a habitability mission, but it's certainly going to learn a lot more about that moon, from which we may or may not be able to derive information about its habitability.
Okay, question number 3. When will you turn the instruments on once it is launched? And also, can you redirect the spacecraft if you find a plume just off course?
Yes. So when exactly they turn on, we'll do checks. We'll turn on the instruments a little while after launch to check them all out, make sure they're all working in space. And then I think they'll be on. Some of the observations will happen before we get in orbit around Jupiter. So we will start getting data fairly early on, which is, of course, very exciting. And we do have the option to change the course. If there is a really interesting interesting feature on the surface, or if we do see a plume and we find that it's safe enough to fly through, NASA was the one that released that image of us flying through one. So, that's definitely in consideration and doable. Of course, we have to weigh all the pros and cons of doing it, right? Because we have a really good plan. We're going to be optimizing our plans with the assumption that we don't necessarily see a plume because we don't know where to find them yet. The ones that we've seen, they have very big uncertainties on exactly where in the surface they might have been emanating. So, of course, we can make tweaks, but we also already have a really great science plan. So we have to kind of weigh those options of, is it worth it to change the whole plan around to go and get closer to that plume? Or maybe, so one thing that's important to note about NASA missions is that that 3 years is sort of the nominal initial mission, but the spacecraft is expected to survive much longer. And so potentially, assuming that NASA says, yeah, go for it, there could be a follow-up part of the mission, a second part of the mission where going through plumes might become more of a priority. Because, it would be a riskier observation to fly through something in case something hits the spacecraft. So there's always that little bit of a risk there too.
All right, question number 4. What kind of life might you expect to find if it is habitable?
I'm hoping, I don't know, anybody see the Europa report? I'm hoping for some like an octopus or some fish. No, I think that would be amazing if we saw something like that. The hope is to see signatures of any kind, the astrobiology side of things. If we saw any kind of signature of the most basic bacteria or forms of life in that sense, that would be in and of itself one of the most exciting discoveries, I think, of all time. So, we're not limiting ourselves to what we think we're going to see or what we're trying to see. But I think when we're talking about is it habitable, we are thinking of some of the more basic forms of life that, maybe started out on Earth in the earliest days as well. But we don't know. That's why we're going.
All right, next question. How many flybys can we expect from the Clipper mission?
So it really depends on the tour, but a lot of the kind of nominal plans right now are about 45 to 50 flybys. And again, that's with that first initial mission. We have a set mission, a set goal, and a set amount of time that we expect everything to work. And that's those 3 years. Anything beyond that is cherries on the top. There's lots of cherries on the top. And so in that case, if we can add those cherries later, we would try to get as many more flybys as we can. The major limiting factor, because this is a solar panel powered mission, so the limiting factor is really that radiation environment and how it's going to be degrading our spacecraft and degrading our instruments.
All right, next question. Could future missions include a companion probe, kind of like how the Cassini-Huygens companionship was?
Great question. So I didn't talk about it here, but there is a lot of talk and a lot of interest and a lot of planning that have already gone into the idea of what's called the Europa lander. And so this would be a spacecraft that would basically land on the surface of Europa. It would not be able to be a very long mission, again, because it's going to sit there in that really high, intense radiation environment. But that would be sort of the next step to understanding more about Europa once we got there. So this spacecraft would land on the surface and it would take all kinds of measurements of the ice and really be more of that astrobiology focused type of mission. So there's hopes for it. There's definitely people planning it and working the numbers and trying to get it proposed and flown. But of course, the budgets for NASA are limited too. And so there's, a competition, there's a lot of really cool places to go in the solar system. And so everyone's sort of trying to fight for their favorite mission kind of thing. So I hope that certainly happens. I think what an important part of Europa Clipper will do is it will really get a great sense of the surface of Europa. So we'll know which regions might be safer for a lander to land on, things like that. And so I think a lander has a more potential of being successful and flying to Europa after we've had this sort of reconnaissance of the surface and understand what Europa's surface structure might look like. That'll help sort of determine maybe the best place for a lander to even go and land.
All right, next question. What end-of-life plans do you expect for the Clipper mission after all the flybys? Like, what is the coup d'etat?
There's some experts out there. So Europa, because it is an ocean world and because it is one of the prime parts of our solar system where we think the existence of life is possible, our biggest no-no is putting any kind of human contamination on the surface of Europa. So we would definitely, once the mission is over, we will dispose of the spacecraft so as to never have it accidentally hit Europa in 10 years from now. We just turn the spacecraft off and we're like, oh, it's just flying away. It's fine. If something happens and the gravity causes it to somehow come back in and hit Europa, we would be really, really mad at ourselves. So the goal will probably be to dispose of the spacecraft in some way. And whether that's through crashing into Jupiter, that's an option like Cassini did on Saturn. or possibly crashing it into one of the other major moons, which I think would be really exciting, especially if the JUICE mission is still out there at the same time and can watch what happens when we crash it in. I think that would be the coolest option. But there's multiple options, but we will dispose of it safely so it doesn't impact Europa.
All right. Are there any more questions? All right. If there are no more questions, thank you again, Sam and Dr. Tracy Becker, for joining us today and to share some of your knowledge. And for everybody, thank you all for joining us. Here's to you. Have a wonderful holiday season. We'll see you again for another Astronomy on Tap in the new year. So here's hopes that 2021 will be better than 2020. So cheers, everybody.
Cheers to that.
Thank you.